Good evening, I am Ishaan Iyer and I'm going to present a topic on how quantum computers can break encryptions. So we'll start with what are quantum computers. Quantum mechanics is a branch of physics that describes the behavior of matter and particles at the smallest levels. Quantum computers are the type of computing device that uses these principles and performs certain types of calculations which are more intensive and more effective than classical computers. Classical computers can process information in either two states, 0 or 1. Quantum computers, on the other hand, use quantum bits or qubits, which can be present in multiple states, also called as superposition. This allows quantum computers to perform many calculations at once. Another key principle of quantum computing is entanglement. When qubits become entangled, the state of one qubit becomes directly related to the state of the another, regardless of the distance between them. This enables the computers to perform certain types of computations much faster than the classical ones. This is the representation of a qubit. It is a complex number with 0 at the top and 1 at the bottom, and it can be present in any state, even simultaneously, which is called superposition. Benefits of a working quantum computer. Quantum computers can provide exponential speed up for specific types of calculations, such as factoring large numbers, searching databases, and even simulating quantum systems. This implies that certain computations that would take an impractical amount, a huge amount of time on classical computers, could be performed much faster than the quantum ones. They also excel at solving optimization problems, which involve finding the best solution among a large number of possible options. Again, they are excel at the ones which requires a lot of repetitions. This has applications in fields such as logistics, finance, and even supply chain. Quantum computers can leverage the principles of superposition and entanglement to perform many calculations simultaneously. This parallelism can lead to significant speed up. With its benefits, there are also threats. Most of its advantages are major threats to popular cybersecurity, encryption, and data privacy algorithms. Encryption methods such as RSA and ECC rely on the difficulty of mathematical problems, such as factoring large numbers. It is too long and tedious for classical computers. I believe with the current RSA standards, it would take 2000 years for a classical computer to break its algorithm, its encryption, whereas quantum computers can do it much faster. This leads to data privacy breaches, as information that is currently considered secure could become vulnerable to unauthorized access, provided the data is stored in encryption methods. This includes not only past communications but also the data archived from long-term security. We are going to talk about how quantum computers breach the RSA algorithm. RSA is an asymmetric encryption algorithm that involves prime factorization, a semi-prime. A semi-prime is a number that is a factor of two prime numbers. And we figure out the prime numbers P and Q. This encryption involves finding the encryption and decryption keys that are found from N, P, and Q. Hence, the N, which is given public, if one can find N and compute its prime factors, they can easily obtain the decryption key and also decrypt the message. RSA relies on the difficulty of factoring the product of the two large prime numbers to secure the communications. The security of this is based on the assumption that the classical computers take too long and it is infeasible for them, especially when the numbers are sufficiently large. Shor's algorithm is how quantum computers break it. This algorithm is an algorithm that is designed to effectively factorize large composite numbers. Factoring large numbers into their prime components is a problem that is very hard for the classical computers, can be solved exponentially faster. Factoring numbers with Shor's algorithm begins with selecting a random integer, a random guess. we random guess and we check if it's a factor of a large prime number. The classically calculated greatest common divisor, which is also known as GCD, of these two numbers, the random number and the target number, is then used to determine whether the target number has already been factored accidentally. For smaller numbers, it is easily done in classical computers, but for larger numbers, a number which is, I think, few lines of this computer, it would take around 2000 years, as I already said. How it works: calculating factors of a large number. We take a random number g and check if it's a factor of n. If it's not a factor of n, we find a p such that g minus g raised to p minus 1 is a multiple of n. This gives us, we can simplify this into two factors. These two can be considered as two factors of m into n, where p is the power that we raise to get this equation. These two, the property is, if these two are not factors of n, they will at least share a common factor. These two will at least share a common factor with n, which is also a very helpful thing, as we can then find the factor using Euclid's theorem. Okay, so how Shor's algorithm is done using quantum computing. Quantum computing uses a concept called superpositioning, where for a given g, we can find all of its powers up till n and find the remainder it gives when finding the mod. And if we measure, suppose we want to measure the remainder to be 3, our output would be a superposition of all the powers that give the remainder 3. And if we measure it, it will give us a random output. Like we are not sure which output will come, but the remainder will always be 3. So that is the advantage of superpositioning, that it can perform several tasks at the same time. Next step is the quantum Fourier transform. It is used specifically in Shor's algorithm to efficiently find the periodicity in the modular exponentiation function. This is a key step in factoring large numbers. When a number is input into a quantum Fourier transform, a superposition of all other numbers is also observed at the output. But each number is given a specific weight or a probability, which when plotted looks like a sine wave. When superposition of numbers is input into the Fourier transform, a superposition of these superpositions is observed and all the destructive interfaces are removed. Hence, when we input the superposition output observed in the Shor's algorithm, we obtain a single value output, which is the period. Here I have shown you the input of one single integer, and it gives the output of all other integers with specific weights. And if you plot those weights, you get a sine curve like this. This is a superposition of 1 and 2. And if you input this into the Fourier transform, you get the output of two sine waves as the superposition of both the graphs. So we use this method to find our period in the Shor's algorithm. We find P by finding the QFT of the Shor's algorithm, and this is done by X. X is our number, and P is the period. So if you input the whole period into the quantum Fourier transform, you get a single output, which would be the period of the thing. And if P is even, we can then find our g raised to p by 2 plus minus 1, which will be used to find the factors of n. If it's not, then it will most likely share a factor. Now we find the factors using Euclid's theorem. Euclid's theorem is a classical algorithm for finding the great GCD of the two numbers. So the two numbers are going to be this one and n. We use this knowledge to find here. This is the current situation of quantum computing. Okay, so once we find the factors of n as p and q, we can then find the encryption key as well as decryption key using the formulas of RSA. The current situation. As of now, there is no quantum computer strong enough to perform Shor's algorithm on large prime numbers. Shows algorithm, which is a quantum algorithm for factoring large numbers, requires a significant number of qubits to factorize large numbers. While there have been demonstrations of small scale factoring, breaking RSA requires a much larger quantum, and again, the current maximum number that can be operated on is 21 and the smallest is 15. That leaves us with a very narrow range to perform any kinds of operation. Quantum computers are susceptible to errors due to environmental factors, and maintaining coherence of qubits over extended periods is a significant challenge. For practical computation, error rates need to be very low and decoherence must be effectively mitigated. Preventive measures. As quantum computing is advancing, we need to find preventive measures also. One method is to implement quantum resistant cryptography. A slow transition into these algorithms are believed to be secure against quantum attacks. It is believed that they are actively being researched and aim to provide security even in the presence of large scale quantum computing. You can diversify cryptographic algorithms and avoid relying solely on a single cryptographic algorithm. By diversifying our portfolio, we can include a mix of algorithms, both classical and quantum, to provide a layered defense against potential attacks. We can even use the quantum key distribution for secure communication. It leverages quantum properties to provide a theoretically secure method for exchanging cryptographic keys. And finally, we need to monitor and keep updated with all the quantum advancements in the industry. As the technologies evolve, we need to be informed about the breakthroughs and advancements. Is blockchain safe? Blockchain is considered to be very safe because it's centralized and uses hashing algorithms. But when you compare it to classical mechanisms, which is very secure because of its hash function and digital signatures, and using Shor's algorithm, this could allow an attacker to forge digital signatures and potentially tamper with transactions. Although hashing is safe from quantum computing, stuff like digital signatures can still be used for attacking. So blockchain is not completely safe. I will proceed with a demonstration for a small prime number, which is n is equal to 15. So I am using the Qiskit, which is an online cloud of IBM. I'm going to use IBM's cloud server to perform a small task on quantum computing. We import the modules of Shor and quantum instance as well as quantum circuit. This is my API key, which is provided by IBM to allow me to use the cloud. This is the basic example of a Shor's algorithm where I input n as 5 and our first guess as 2. It gives us the factors of 3 and 5, which we know are true. Now I'm going to show you the whole process of cracking a prime number. So first we'll define a modular function which takes input as a and power, and we make a quantum circuit and we give this formula inside, which is a raised to the power mod 15. 15 is the one we need to find. We give our two inputs, which is the large prime number, supposedly large prime number is 15. Our initial guess is 7. We define a Fourier transform function and give this formula as the input. We then proceed to make a quantum circuit, and we append, and in this sentence we append the modulus as well as the transform, and we plot the diagram. So this diagram shows us the steps and all the plottings of the Fourier transform, and all the steps like this is 7 power 1 mod 15, 7 power 2 mod, and 4, 8 and so on. This is 16, 32, 64. It will go on, it will keep on iterating, and this is our Fourier transform. Fourier transform basically finds the probabilities, and in this section I've printed the 3 most probable powers of G which are likely to give the answer. We have the elements as 1, 2 and 4, For example purposes, I'm going to take 4. By taking 4, we can now test out 7 power 4 by 2 because the formula is g power p by 2 plus minus 1. So we get 7 powers 2 plus minus 1, which is 49 plus minus 1. So you get 7 power 2 plus 1 is 50 and minus 1 is 48. Now if your factor is 50, you get 5, 2 as the prime factors. And if you factor is 48, you get 3 and 2 as the prime factors. By with the common factors it shares with 15 are 5 and 3. Hence we have found out the 2 prime factors of 15, and we can now proceed to crack the RSA algorithm by finding the encryption and decryption keys. Thank you.